All right, today we are going to take a look at another type of volume. But first, just real quick, another visual on what we just did. Okay, finding volume of figures where we know what the cross section is. Okay, so let's say we want to find so these are our two curves, this green curve and this red curve, and we want to find the volume of a figure whose base is this region right here. Okay, so if we look at this picture, right, the base of the figure is this region right here. And let's first say that I know the regions, or the cross sections are semicircles, right? So this is what that figure would look like, right? This figure. And I can see that no matter where I slice through, the cross section is a semicircle. Okay, same thing for an equilateral triangle, right? We would get some figure that looks like this. Okay, and I can see that no matter where I slice through it, no matter where I slice through it, the cross section is an equilateral triangle. Right? And we looked at all these different types of shapes. Right here, no matter where I am, the cross section is a square. Right? So we get some figure that looks like this. All right. Today, we're going to take a look at something like this. Okay, so come on. There we go. All right. So let's say I've got my function is the square root of x. So we can see in this purple graph right here, here's my square root of x, and then here's a three-dimensional graph. What we're going to do today is say, well, what if I take this curve and revolve it around either the x or the y-axis? Okay, then we can create this new solid. Okay, we get something that looks like this, and in this visual, it's hollow, but we're assuming that what we're creating is a solid object. It's hollow just so we can kind of see what this figure looks like. All right. So we're creating something that looks like this. Now, and we can do this with any function, right? Say we take a quadratic, x squared plus 1, right? And I take that figure, right? So here's that quadratic, right? And we can see it in this three-dimensional representation as well. Let's say I take that just from 0 to about 2 and rotate that around the x-axis. Okay, now again, we're assuming that the inside is solid, but we would create some three-dimensional figure that looks like this. All right. So that's what we're going to do today. Now, if you remember back here, our goal was to write an equation for the cross section, okay, the area of a cross section, and then integrate that. It's going to be the same thing today. Our goal is going to be to write an equation for the area of a cross section here, and then integrate that on whatever bounds that we want. Well, if I'm revolving something about an axis, hopefully we can see no matter where I would slice through this, the cross section is going to be a circle. So I actually think that what we're going to do now, solids of revolution, is a little bit simpler than the known cross section idea that we just finished. Okay, no matter what axis I'm revolving around, and we'll look at revolving about the x-axis and the y-axis. Okay, the cross section of one of these figures that's created is going to be a circle. All right, so let's look at our notes here. Okay, this first example, we've got a real simple region. So here's my xy plane, and I'm taking this triangle created by this line. So this line is x plus 3y equals 6, and I want to rotate this around the y-axis. So if I take this triangle and rotate it around the y-axis, I'll get a cone. All right, so I know the volume of a cone is 1/3 pi r squared h. And in this case, my radius, okay, so if I'm revolving about the y-axis, right, the radius of the base of the cone would be 6, this length right here. So if I do 1/3 times pi times 6 squared times my height, which would be 2 in this case, I would just get 24 pi. Right? So in a case like this, it's pretty straightforward to just use a geometric formula. But we're going to use this example to show how we can also find this area using find this volume using integration, and then go into some uglier looking figures. All right, so what we want to think about is that cross-section idea. All right, so if I cut out a cross-section here, we can see it's going to be a circle, right, or a disc. So if I think about the volume of this disc, the volume of the area of a circle is pi r squared h. Well, the radius in this case is the distance from this line to the y-axis. That's whatever the x value is. Okay, now if our line, this line is x plus 3y equals 6, right? So if I solve this for x, I just get x equals negative 3y plus 6. So this distance, right, the distance from the line to the y-axis is negative 3y plus 6. If I want to find the volume of this cone, I need to write an area formula. Okay, so an area of this circle. If I'm saying the volume of my, well, I want to think about this more as area, right? The area of a cross-section. So the area of my cross-section is pi times r squared, right? If this is going to be a circle. So if we think about this x distance is negative 3y plus 6, my area function for this cross-section, now I'm writing this in terms of y, right? So I'm going to say a of y is equal to pi times the radius squared. So negative 3y plus 6 squared. So that is the area of one of these circles. No matter where I take a cross-section, I'm going to have pi times the radius squared. So now if I want to find the volume, I'm just going to integrate my area function. So if I want to find the volume from 0 to 2, and remember we're talking about the y-axis, so that's why I'm integrating from 0 to 2. Right? My setup would look like this. So pi times, let me write it like this, negative 3y plus 6 dy. Now I could just pull that pi out front when I integrate because pi is just a constant. And this would be a, oops, I forgot my square, didn't I? Pi times the radius squared. So this would be a fairly straightforward integral to do by hand. Right? It would probably be easiest to just go ahead and square this binomial instead of trying to do a u substitution. So if I do that, if I pull my pi out front, square what we have here, that'll end up being positive 9y squared minus 36y plus 36 dy. Now we would integrate, right? Take the antiderivative of each piece individually, and that pi will just stay out front. So pi times, this would be 3y squared minus 18, or I'm sorry, 3y cubed minus 18y squared plus 36y, and I want to evaluate that from 0 to 2. So if we plug all of those values in, pi times 3 times 2 cubed minus 18 times 2 squared plus 36 times 2. Then if I plug 0 in, obviously all these would be 0. So I'm not going to write all that out. And if we do this calculation, we end up with 24 pi. Right? So I know it's probably a little confusing now why we integrated with respect to y and not x. So let's try to explain that a little bit here. Actually, jump down to here. Whenever I am revolving around a horizontal axis, okay, and for today, what that just means is the x-axis. Okay, the x-axis is horizontal, right? So if I'm revolving about the x-axis, I'm going to have my function in terms of x. If I'm revolving around the y-axis, I want my function in terms of y. So I would here, okay, I'm integrating the area function pi times my function in terms of x squared, so pi r squared. Here I'm integrating pi times my radius in terms of y squared. All right, so let's jump into another example here. So here I'm taking y equals negative x plus 1 and revolving that about the x-axis. So they don't give me any bounds here. I'm going to have to figure out what my bounds should be. So let's graph this function. Plus 1 means I've got a y-intercept of 1, and then I've got a slope of negative 1. So I would go down 1, right 1, and I would just end up with a line through here. So let's get a nice line that almost matches up. Fix that. There we go. So here's my line. Now I want to take this triangle that we created and revolve this around the x-axis. So I will get a cone that's, the mouth facing to the left here, and then my tip of the cone would be right here. That's what's going to happen when I revolve this about the x-axis. So I can see that my bounds are going to be 0 and 1. So everything's in terms of x. We're looking at the x-axis for our bounds, and we want our function in terms of x. Well, it already is, right? It's solved for y. So my radius, okay, this, if I think about the cross-section, okay, well, the radius would be this distance. Well, that distance is the function itself, negative x plus 1. So if we think about this becoming a circle, right, the radius then would be negative x plus 1. So if I want to write my area function, a of x would be pi times the radius, negative x plus 1 squared. So then to integrate this, to set up my integral, I'm going to have 0 to 1, and I can just pull that pi out front, negative x plus 1 squared dx. So again, if we're going to do this by hand, it's probably easiest to go ahead and square this binomial. So that would just become positive x squared minus 2x plus 1 dx. Then take the antiderivative of each piece individually. So we'll have pi times 1/3 x cubed minus x squared plus x, evaluated from 0 to 1. So then I'm plugging in 1. So this would just be 1/3 times 1 minus 1 squared is 1 plus 1 minus 0. Right? So we just end up with 1/3 minus 1 plus 1. So those would cancel out. Times pi. We just end up with 1/3 pi, or pi over 3. So the volume of this figure, if created by revolving this triangle about the x-axis, is pi over 3. All right? Let's take a look at the next one here. Okay, this one isn't quite as nice, right? But this is what we looked at in our first example here, right? Taking the square root of x and revolving this about the x-axis. So this is what that figure is going to look like. Okay, it's going to look something like this. And again, we're assuming this is a solid figure. All right. So our setup, okay, I guess let's first kind of sketch this out. Hopefully we know the square root of x does something like this and then just keeps growing to infinity. So they tell us I'm going from 0 to 4. Okay, they tell us those are our bounds. And then this is the square root of x. So this distance, right, this is my radius. If I think about revolving this around the x-axis, this distance is my radius of my cross-section. So if I want to write the area of a cross-section, I'm going to say that it's pi times the radius squared. So pi times the square root of x squared, which is just pi times x. So if I want to find the volume of this figure, I'm going to integrate my area function. So we know our bounds are 0 and 4. I can pull my pi out front, and I'm just integrating then x dx. So this is a pretty easy one to do. Antiderivative of x is 1/2 x squared, and I'm evaluating that from 0 to 4. So I will have pi times 1/2 times 4 squared. Then if I plug in 0, I just get 0. So 4 squared is 16, divided by 2 is 8, times pi. We get the volume of this figure is 8 pi. All right. Now, let's look at one where we revolve about the y-axis. All right. So in example 3 here, I'm taking y equals x squared and revolving this about the x-axis. So again, they say we're just going from 0 to 4. So I'm just going to draw this half of the parabola. And now I'm going to take this and revolve it about the y-axis. Okay, so we'll end up with, let's see, if we assume that 4 is here, going from 0 to 4, we will end up with some figure that looks like this, right? If I take this and revolve it all the way around, I'm going to get something like this. Okay, so what I want to do here is say, well, I want everything in terms of y. So I need to solve this for x. If I'm revolving about the y-axis, I need to solve this equation for x. So to do that, right, we just end up with, we would technically have plus or minus the square root of y, but here I just need the positive root because I'm going to be revolving it. So my area function, and now this is in terms of y, is going to be pi times my radius squared. Well, that's just pi times y. So this is actually the exact same problem as what we just did. Right? We just kind of turned it on its side. Here we had y equals the square root of x. Here we have x equals the square root of y. And we're taking our same bounds. So I'm going to actually end up with the same figure here. Right? So if we set up our integral, pull out the pi, times the integral from 0 to 4 of pi, oops, I already wrote my pi, of y dy. So the process is exactly the same as the last problem. We don't need to work it out again. We know that we're going to get 8 pi. Okay, so the key is just figuring out what the radius will be. In this case, we said the radius was this distance from the curve to the y-axis. Okay, So all we're doing is saying the radius of our cross section, which is our circle, is the function itself. So we'd have pi times the function squared. Let's do one more example here. So here we're taking y equals e to the x and revolving about the x-axis from 0 to 2. So our functions in terms of x, we're good. So e to the x will do something like this. So if we're just going from 0 to 2, I'll just draw this piece. Say that 2 is here. So I'm taking this region right here and revolving it about the x-axis. So if I want to think about writing my area function of a cross-section, it's going to be pi times the radius, which is just e to the x squared. Now, if I've got a power to a power here, we know we can clean that up a little bit and just multiply those powers together. So this would just be e to the 2x. So if I want to integrate this, we're told that our bounds are 0 to 2. So to find this volume, integrating from 0 to 2 of my function, so I can pull the pi out front, and then we just have e to the 2x dx. If I want to do this by hand, we would actually want to come off to the side and do a little u substitution here. So we can say that u would be 2x, my du would then be 2, but I just want it to be 1, right? I've got nothing in front of the e to the 2x. So I would need to multiply both sides by 1/2. So we end up with 1/2 du equals 1 dx. So then we could actually just go ahead and evaluate u of 0. So u of 0, if we want to go ahead and change our bounds, would be 2 times 0, which is 0, and then u of 2, which would be 2 times 2, so that would be 4. So I can change this entire problem to be a u substitution problem. So if I do my u substitution here, my new bounds are 0 and 4. That pi will still be out front there, but then I will have e to the u times 1/2 du. So I can pull that 1/2 out front as well. That's a u out of 4. So the antiderivative of e to the u du is just e to the u, right? So I'll have this pi over 2 out front times e to the u evaluated from 0 to 4. Then I can just plug in my 0 and my 4. So I'll have pi over 2 times e to the 4th minus e to the 0. Now in this case, this is not 0. Okay, I'm still seeing some people make this mistake, especially on the last take-home test. E to the 0 is not 0. E to the 0 is 1. Okay, so make sure that you're not making the mistake of making this go away. So this would be the same as pi over 2 times e to the 4th minus 1. All right, so this is our final answer here if we want an exact number. All right, so just to recap, if I'm finding the volume of a solid created when I revolve a region about an axis, we're just saying that that cross-section is pi times the radius squared. And the radius is just the function itself, right? So it's that distance from the function to the x-axis, which we say is just the function. Then I integrate that pi r squared, that area of the cross-section. And that gives me the volume of that figure, okay? Give the homework a try now. And we will, send me any questions through Remind. Please send me questions through Remind or email, whichever you prefer. And then I will be back tomorrow.